There is something surrounding you right now, something you cannot feel, cannot see, and will never directly touch. Yet without it, you would not exist. It flows through your body, through the walls around you, through the earth itself, completely unnoticed. And strangely, it outweighs everything you've ever seen. Tonight, you are not just listening to a story about space. You are drifting into one of the deepest mysteries ever discovered. A mystery that quietly shapes every galaxy, every star, and every moment of your existence. Welcome to Velarin's Sleepy Space Mysteries. And if you've ever wondered how the universe builds itself from nothing, you might remember our journey through the strange birth of cosmic structure in another video, where we explored how galaxies first began to form out of darkness. Tonight, we go even deeper into that darkness, because what we once believed was everything turns out to be almost nothing. For most of human history, we assumed reality was simple. The stars in the sky, the planets, the glowing clouds of gas, that was the universe. But as our instruments grew more precise, something unsettling began to emerge. The universe didn't behave the way it should. Galaxies spun too fast. Clusters held together too tightly. Light bent in ways that made no sense. It was as if an invisible hand was guiding everything, quietly pulling the cosmos into shape. And that invisible presence now has a name: dark matter, a substance that does not shine, does not reflect, does not interact with light at all, and yet makes up most of the matter in existence. As you settle in, let your mind drift gently into this mystery. And if you've ever wondered how the universe builds itself from nothing, you might remember our journey through the strange birth of cosmic structure in another video, where we explored how galaxies first began to form out of darkness. Tonight, we go even deeper into that darkness. For most of human history, we assumed reality was simple. The stars in the sky, the planets, the glowing clouds of gas, that was the universe. But as our instruments grew more precise, something unsettling began to emerge. And if you enjoy exploring these quiet cosmic secrets, consider subscribing, leaving a like, and turning on the bell so you don't miss future journeys. You can also join as a member to support the channel. To understand how something invisible can dominate the universe, we have to begin in a place where everything still seemed predictable. A time when astronomers believed that if you could measure what you could see, you could understand everything that existed. It was a comforting idea, one rooted in centuries of observation, where light was our only guide and the stars told us their secrets through the glow they emitted. But this comfort began to unravel in the early 20th century, when careful measurements revealed that the universe was not behaving as expected. The first real crack in this illusion appeared in 1933, when an astronomer named Fritz Zwicky turned his attention to a distant collection of galaxies known as the Coma Cluster. This cluster, containing over 1,000 galaxies, was bound together by gravity, each galaxy moving in a vast cosmic dance around a shared center of mass. Zwicky's goal was simple in theory: measure how fast these galaxies were moving, then calculate how much mass must be present to keep them from flying apart. The logic was the same as understanding planets orbiting a star. Faster motion implies stronger gravity, and stronger gravity implies more mass. Using the Doppler effect, a method that detects motion through shifts in light toward red or blue wavelengths, Zwicky meticulously calculated the speeds of these distant galaxies. But when he compared those speeds to the visible matter in the cluster, something deeply unsettling emerged. The galaxies were moving far too fast. So fast, in fact, that if only the visible stars and gas were present, the cluster should have torn itself apart long ago. And yet it hadn't. It remained stable, as if held together by something unseen, something massive, something quietly exerting gravitational influence without revealing itself in any other way. Zwicky realized that the visible matter accounted for only a tiny fraction of what must actually be there. He proposed that an enormous amount of invisible mass was hidden within the cluster, providing the extra gravity needed to hold everything together. He called it dark matter, not because it was simply dark like the night sky, but because it was completely invisible to every instrument available at the time. It did not emit light, reflect light, or block light. It simply existed, silently shaping the motion of galaxies. But his idea was so radical, so far removed from the accepted understanding of the universe, that most scientists ignored it. Some assumed he had made an error in his calculations, while others dismissed the concept entirely. After all, suggesting that most of the universe was made of something no one could see sounded almost absurd. And so, for decades, the idea of dark matter lingered quietly at the edges of astronomy, neither confirmed nor completely forgotten. Yet the mystery did not disappear. It waited, and as time passed, new observations began to reveal the same strange pattern, not just in distant clusters but much closer to home, within the very galaxies we can see in the night sky. The universe, it seemed, was trying to tell us something. Something subtle, something persistent, something impossible to ignore forever. And slowly, piece by piece, scientists began to realize that Zwicky may have glimpsed a truth far larger than anyone had imagined. A truth that would eventually reshape our entire understanding of reality itself. The quiet suggestion that most of reality might be invisible did not fully take hold until decades later, when a new generation of astronomers began looking not at distant clusters, but at the graceful spiral galaxies drifting much closer to us. Among them was Vera Rubin, a scientist whose patience and precision would slowly turn a controversial idea into an unavoidable truth. Rubin was not studying entire clusters like Zwicky had done. Instead, she focused on how individual stars move within a single galaxy, particularly our neighboring spiral Andromeda galaxy. At first glance, galaxies seem simple. A bright central bulge, surrounded by sweeping arms of stars, all rotating together like a cosmic whirlpool. Based on everything known about gravity, the expectation was clear. Stars closer to the center, where most of the visible mass resides, should orbit faster, while stars farther out should move more slowly, just as the outer planets in our solar system drift more gently around the sun. This expectation was not guesswork. It was rooted in centuries of physics, stretching back to Isaac Newton and his understanding of how gravity governs motion. Rubin and her colleague, Kent Ford, developed highly sensitive instruments capable of measuring the speed of stars with extraordinary accuracy. Night after night, they observed the faint light from distant stars, carefully analyzing subtle shifts in wavelength to determine how fast those stars were moving as they orbited the galactic center. And what they found was not just surprising, it was deeply unsettling. The stars at the outer edges of the galaxy were not slowing down. They were moving just as fast as the stars near the center. This defied everything that classical physics predicted. If only visible matter were present, those outer stars should not have been able to maintain such high speeds. They should have drifted away into the darkness of intergalactic space, escaping the weak gravitational pull of the galaxy's visible mass. But they didn't. They remained bound, held tightly in orbit as if an unseen force was anchoring them in place. Rubin did not stop with one galaxy. She observed many, and everywhere she looked, the same pattern appeared. Flat rotation curves, where velocity remained constant even far from the galactic center. It was as if every galaxy was embedded within a vast, invisible halo of mass, extending far beyond the glowing stars we could see. Slowly, the implications became impossible to ignore. If galaxies were surrounded by these enormous halos, then the visible portion of a galaxy was only a small part of a much larger structure. The luminous stars were merely the bright core of something far more massive and completely hidden. The idea that Zwicky had proposed decades earlier was no longer a strange anomaly. It was becoming a consistent feature of the universe. Yet this realization brought with it a deeper mystery. If this invisible matter was everywhere, shaping the motion of galaxies and holding them together, then it must be incredibly abundant. In fact, calculations suggested that there was far more of this unseen substance than there was of ordinary matter. Everything we could see, every star, every planet, every cloud of gas, might represent only a small fraction of what actually exists. The rest remained hidden. Imagine standing in a vast, dark ocean, where only a few glowing lights float on the surface. You might think those lights are everything, but beneath them lies an immense, unseen depth, quietly supporting and shaping everything above. This is what the universe began to look like through Rubin's observations. A place where the visible is merely a trace, a thin layer resting atop something far greater and far more mysterious. And yet, even as this idea gained acceptance, it raised a question that still echoes today, a question that we will return to again and again as we drift deeper into this story. If this invisible matter surrounds every galaxy, if it outweighs everything we can see, if it governs the motion of the cosmos itself, then what is it actually made of? As this quiet realization settled into the scientific world, a subtle shift began to take place. The question was no longer whether something invisible existed, but how deeply it shaped the universe itself. Because if this unseen mass surrounded every galaxy, then it was not just a hidden detail. It was the foundation upon which everything visible was built. To explore this idea, scientists began looking not only at how galaxies move, but at how the entire universe evolved over time. And what they found added another layer to the mystery, something even more profound than fast-moving stars or stable clusters. It suggested that without this invisible substance, the universe as we know it might never have formed at all. To understand why, imagine the early universe not long after the Big Bang. At that time, everything was nearly uniform, a smooth sea of energy and particles spread out in all directions. There were no galaxies, no stars, no planets. Just tiny variations in density, slight differences so small they would seem insignificant, like faint ripples on an otherwise calm surface. These tiny variations are still visible today in the faint afterglow of the Big Bang, known as the cosmic microwave background, which acts like a snapshot of the universe when it was only a few 100,000 years old. In this early state, ordinary matter, the kind that makes up atoms, was not free to clump together easily. It was constantly interacting with radiation, pushed around by light itself, almost like dust suspended in a bright beam, unable to settle. If only this ordinary matter had existed, gravity would have struggled to gather it into dense structures before the universe expanded too much. Galaxies might never have formed. The cosmos could have remained a thin, diffuse fog, with no stars to light it, no planets to host life, no structure at all. But something else was there, something that did not interact with light, something that was not pushed around by radiation. Dark matter. While ordinary matter was still being stirred by energy, dark matter remained unaffected, quietly responding only to gravity. It began to gather into clumps long before atoms could settle, forming invisible structures throughout the universe. These clumps acted like gravitational seeds, pulling in ordinary matter once the universe cooled enough for it to fall inward. Over time, these regions grew denser, attracting more material, gradually forming the first galaxies. In this way, dark matter did not just accompany the formation of structure. It guided it, it shaped it, it made it possible. Every galaxy you can see tonight, including our own Milky Way, is believed to sit within a vast halo of dark matter, an enormous, invisible sphere extending far beyond the glowing stars. The visible galaxy is just the bright center, like a small island within a much larger, unseen landscape. This idea transforms how we think about the universe. It suggests that what we perceive, the stars, the nebulae, the glowing galaxies, is only the surface of a deeper reality. Beneath it lies an intricate, invisible framework, quietly holding everything together. Scientists sometimes describe this framework as the cosmic web, a vast network of filaments and nodes stretching across unimaginable distances. These filaments, composed mostly of dark matter, connect clusters of galaxies like threads in an enormous, three-dimensional web. Between them lie vast voids, regions almost completely empty, where very little matter exists at all. The structure is not random. It is organized, patterned, shaped by gravity acting over billions of years. And at the heart of this structure is dark matter. Simulations of the universe, run on powerful computers, have shown that when dark matter is included, the results closely resemble what we observe in the real cosmos. Galaxies form in the right places, clusters emerge, filaments stretch across space. But when dark matter is removed from these simulations, the structure collapses. Galaxies fail to form properly. The universe looks nothing like what we see. This is one of the strongest pieces of evidence that dark matter is not just a theoretical idea, but a real and essential component of reality. It is not something we can ignore or replace easily. It is woven into the very fabric of cosmic evolution. And yet, despite all of this evidence, despite its overwhelming influence, we still do not know what dark matter actually is. We can see what it does. We can map where it must be. We can calculate how much of it exists. But its true nature remains hidden, just beyond the reach of our instruments and our understanding. And so the mystery deepens, because the more we learn about this invisible presence, the more it begins to feel like the universe is built upon something we cannot yet fully comprehend. By now, a quiet pattern has begun to emerge, one that feels almost paradoxical the longer you sit with it. The universe appears luminous, filled with stars and galaxies that glow across unimaginable distances. Yet the true weight of reality lies in something that never shines at all. And while gravity has allowed us to trace the presence of this invisible mass, there is another, more delicate way the universe reveals its hidden structure, not through motion, but through the bending of light itself. This phenomenon, known as gravitational lensing, arises from the deeper understanding of gravity described by Albert Einstein. Instead of thinking of gravity as a simple force pulling objects together, Einstein described it as a curvature of space itself. Massive objects warp the fabric of space-time, and anything moving through that region, including light, follows the curved path. In everyday life, this effect is too small to notice. But on cosmic scales, where galaxies and clusters carry immense mass, the bending becomes visible. When light from a distant galaxy passes near a massive object on its way to Earth, its path is distorted. The galaxy may appear stretched, smeared into arcs, or even duplicated into multiple images. In some cases, the alignment is so precise that the light forms a perfect ring around the foreground object, a phenomenon often called an Einstein ring. These distortions are not random. They are precise, measurable, and deeply informative. By carefully studying how light is bent, astronomers can calculate how much mass must be present to create the observed distortion. And once again, the results reveal something unsettling. The amount of mass required is far greater than what can be seen. Even when accounting for all the stars, gas, and dust within a galaxy cluster, there is still not enough visible matter to produce the observed lensing effects. Something else must be contributing, something invisible, yet massive enough to bend light across millions of light years. In this way, gravitational lensing becomes a kind of cosmic map, allowing scientists to trace the distribution of dark matter directly. Instead of inferring its presence from motion alone, they can now see its influence in the warped images of distant galaxies. The result is astonishing. These maps reveal enormous, cloud-like structures of mass, far larger than the visible galaxies embedded within them. The galaxies themselves appear like small lights floating inside vast, invisible halos. One of the most striking examples of this comes from a system known as the Bullet Cluster. This is not a single cluster, but two galaxy clusters that have collided with each other in a dramatic cosmic event. When astronomers observed this collision, they noticed something extraordinary. The visible matter, primarily hot gas emitting X-rays, had slowed down and collected near the center of the collision, as you might expect from two clouds of gas crashing into each other. But when they mapped the mass using gravitational lensing, they found that most of the mass was not in the center at all. Instead, it had passed straight through the collision, continuing onward with the galaxies themselves. This meant that the majority of the mass did not behave like ordinary matter. It did not collide, did not slow down, did not interact in the same way. It simply moved through, unaffected except by gravity. This separation between visible matter and total mass provided some of the strongest evidence yet that dark matter is not just a theoretical construct, but a real physical component of the universe with its own distinct properties. It behaves differently from anything we are familiar with. It does not clump like gas, does not emit light like stars, does not interact electromagnetically at all. It is, in a sense, ghost-like, passing through both ordinary matter and itself with almost no resistance. And yet, despite this elusive nature, its gravitational influence is undeniable. It shapes the paths of galaxies, bends the light of distant stars, and anchors the largest structures in existence. At this point, the mystery deepens once more, because we are no longer asking whether dark matter exists. The evidence from motion, from structure, and now from light itself has made that clear. Instead, the question becomes far more intimate, almost philosophical in its tone. If something so dominant can exist without interacting with light, without revealing itself directly in any way we can perceive, then what else might exist beyond the limits of our senses? And perhaps more importantly, how do we begin to search for something that seems designed to remain hidden? So now we arrive at a strange turning point in the story, a place where the universe has revealed just enough for us to feel certain that something vast and invisible is there, but not enough for us to truly understand what it is. And when science reaches a boundary like this, when observation can only take us so far, the next step becomes a different kind of exploration. Not just looking outward, but imagining inward, asking not only what we can see, but what could exist beyond what we are capable of seeing. Because if dark matter does not emit light, does not absorb it, does not reflect it, then it must exist outside the entire system of perception that has guided astronomy for centuries. Everything we have ever learned about the universe has come through light in one form or another. From visible starlight to radio waves, from infrared heat to high-energy gamma rays, every telescope we have ever built is, in essence, a translator of light. But dark matter does not speak that language. It remains silent across the entire electromagnetic spectrum. And this silence forces a difficult realization. If we cannot detect it through light, then we must search for it in entirely different ways. This is where the story becomes more experimental, more grounded in Earth-based efforts to capture something that rarely interacts with anything at all. Scientists began designing detectors not to see dark matter, but to feel its presence indirectly, to wait patiently for the rare moment when a dark matter particle might brush against ordinary matter and leave behind the faintest trace of energy. Imagine trying to detect a single grain of sand drifting through a vast, empty room, except the grain can pass through walls, through objects, even through you without stopping. That is the challenge researchers face. The Earth itself is constantly moving through a halo of dark matter as our galaxy drifts through space. This means that, in theory, dark matter particles are passing through your body right now, passing through the ground beneath you, passing through everything, endlessly, silently, without interaction. And yet, just occasionally, perhaps once in a very long time, one of these particles might collide with an atom. That collision would be incredibly subtle, releasing a tiny amount of energy, almost imperceptible, but just enough to be detected under the right conditions. To capture such rare events, scientists have built experiments deep underground, far away from the noise of cosmic radiation that constantly bombards the surface of the Earth. One example is the LUX Zeppelin experiment, located deep beneath layers of rock that act as a natural shield. These detectors are designed with extraordinary sensitivity, capable of detecting even the faintest flashes of light or tiny vibrations caused by particle interactions. Inside these detectors, materials like liquid xenon are used because they respond in very specific ways when struck by particles. If a dark matter particle were to collide with a xenon atom, it could produce a brief flash of light, followed by a tiny electrical signal. By measuring these signals carefully, scientists can attempt to distinguish genuine dark matter interactions from background noise. But despite decades of effort, something remarkable has happened. Nothing has been definitively detected. The detectors have grown larger, more sensitive, more refined. Yet the signals remain elusive. Each experiment narrows the possibilities, ruling out certain types of particles, certain interaction strengths, certain theoretical models. But the answer itself remains just out of reach, like a shadow that retreats the closer you try to approach it. This has led to an expanding landscape of ideas about what dark matter might be. Some theories suggest it could be composed of entirely new particles, ones that have never been observed before. Others propose more exotic possibilities, including fields that permeate space or objects formed in the earliest moments of the universe. There is even the possibility, still debated quietly among scientists, that our understanding of gravity itself may not be complete, that what we interpret as dark matter could instead be a subtle flaw in how we describe the laws of motion on cosmic scales. And yet, despite these uncertainties, one thing remains consistent. Every line of evidence, from galaxy motion to gravitational lensing to the large-scale structure of the universe, continues to point toward the same conclusion. Something unseen is there, something massive, something essential. As we come to the end of this part, let that idea settle gently in your mind. You are not just living in a universe filled with stars and galaxies. You are moving through a vast, invisible ocean, one that shapes everything around you without ever revealing itself directly. And somewhere within that quiet darkness, the answer is waiting. As you drift further into this quiet mystery, something begins to shift in the way you see the universe. Because by now, dark matter is no longer just an invisible substance hiding in the background. It has become something deeper, something structural, something that quietly defines the shape of reality itself. And to understand this next layer, we need to gently zoom outward, far beyond individual galaxies, beyond clusters, beyond even the local regions of space we usually imagine. We need to step back far enough to see the universe not as scattered points of light, but as a vast, interconnected system. When astronomers began mapping the positions of millions of galaxies across the sky, they expected randomness, a kind of cosmic scattering where galaxies were distributed evenly in all directions. But that is not what they found. Instead, a pattern emerged, subtle at first, then unmistakable. Galaxies were not spread out evenly. They were arranged along enormous filaments, forming long, thread-like structures stretching across hundreds of millions of light-years. Where these filaments intersected, dense clusters formed, massive gatherings of galaxies bound tightly together by gravity. And between these structures, there were vast empty regions, known as voids, where almost nothing existed at all. This pattern is known as the cosmic web, and it is one of the most beautiful and mysterious structures ever discovered. But here is the part that makes it even more extraordinary. The visible galaxies, the ones we can actually see, are not the web itself. They are only the glowing traces along its edges. The true structure, the underlying framework that holds everything together, is made mostly of dark matter. Imagine a vast, three-dimensional spider web stretching across the universe, invisible except for the tiny droplets of light that cling to its threads. Those droplets are the galaxies. The web itself remains unseen. Scientists have used powerful simulations to recreate this structure, feeding in the laws of gravity and the known properties of matter, then allowing the virtual universe to evolve over billions of years. When dark matter is included in these simulations, the results are strikingly similar to what we observe in the real cosmos. Filaments form naturally. Clusters emerge at intersections. Voids expand between them. The universe organizes itself into this intricate web-like pattern. But when dark matter is removed from the equations, the structure collapses. The filaments do not form properly. The clusters are weaker. The universe becomes far less organized, lacking the complexity we actually see. This tells us something profound. Dark matter is not just present. It is necessary. It acts as the scaffolding upon which the universe is built, guiding the formation of structure from the earliest moments after the Big Bang. And yet, even as we map this cosmic web, even as we trace its filaments and measure its vast emptiness, we are still only seeing its outline. The true substance remains hidden, its nature still unknown. This creates a quiet tension in our understanding. On one hand, we can describe the universe with remarkable precision. We can map galaxies across billions of light years, simulate their formation, predict their motion. On the other hand, the majority of the matter responsible for this structure remains completely invisible, known only through its effects. It is as if we are reading a story where most of the words are missing, yet somehow we can still follow the plot. And this brings us back to a question that has been quietly echoing since the beginning of this journey. If dark matter forms the skeleton of the universe, if it determines where galaxies are born and how they evolve, then what kind of substance could possibly play such a role while remaining entirely unseen? To answer that, we must move away from the largest scales and begin looking inward again toward the smallest building blocks of reality. Because somewhere, hidden within the fabric of space itself, the true identity of dark matter is waiting to be discovered. As we begin to move inward, away from the vast cosmic web and toward the smallest scales of existence, the mystery of dark matter takes on a different feeling, less like a distant structure, and more like a quiet presence woven into the very fabric of reality. Because if dark matter is not made of the same atoms that form stars, planets, and people, then it must belong to a deeper layer of physics, one that operates beneath everything we are familiar with. To explore this, scientists have turned to the world of particle physics, where matter is no longer thought of as solid objects, but as tiny, fundamental particles interacting through invisible forces. In this realm, even ordinary matter becomes something strange. Atoms are mostly empty space, with electrons moving in probability clouds around a dense nucleus, and the nucleus itself made of even smaller particles called quarks. These particles interact through forces that govern everything from the structure of atoms to the energy of stars. And for decades, physicists have built a framework known as the Standard Model, a theory that describes all known particles and forces with remarkable accuracy. But there is a problem. Dark matter does not fit anywhere within this model. It is not made of protons or neutrons. It is not composed of electrons. It does not interact through electromagnetism, which is why it does not emit or absorb light. It does not appear to participate in the strong nuclear force, which binds atomic nuclei together. And if it interacts through the weak nuclear force at all, it does so rarely that detecting it has proven extraordinarily difficult. This leaves us with a quiet but profound conclusion. Dark matter must be something entirely new, a form of matter that exists outside the framework that explains everything we can directly observe. One of the leading ideas for many years has been the existence of particles known as WIMPs, or weakly interacting massive particles. These hypothetical particles would have mass, allowing them to exert gravitational influence, but would interact only through the weak force, making them extremely difficult to detect. In theory, WIMPs could have been created in the early universe in just the right abundance to account for the dark matter we observe today. It is an elegant idea, one that fits neatly into certain extensions of the Standard Model, including theories that suggest every known particle has a heavier counterpart. But as the years have passed, and experiments have grown more sensitive, the silence has continued. Detectors have searched for the faint signals of WIMPs interacting with ordinary matter, and found nothing definitive. Each null result narrows the possibilities, quietly closing doors that once seemed promising. And so, attention has begun to shift toward other possibilities, ideas that once seemed more speculative, but are now taken seriously as potential answers. One of these is the concept of axions, incredibly light particles that would behave less like individual objects and more like a subtle, oscillating field filling all of space. Unlike WIMPs, which are imagined as particles moving through the universe like invisible bullets, axions would be more like a gentle background presence, vibrating softly at a frequency determined by their mass. Detecting such a field requires entirely different techniques, often involving strong magnetic fields and highly sensitive instruments designed to convert these oscillations into measurable signals. And while no confirmed detection has been made, the search continues, growing more refined with each passing year. There are also even more exotic ideas. Some scientists have proposed that dark matter could consist of primordial black holes, formed in the chaotic moments after the Big Bang, long before stars and galaxies existed. These black holes would be small, dark, and difficult to detect, yet massive enough to contribute to the gravitational effects we observe. Others have suggested the existence of an entire hidden sector of physics, a parallel set of particles and forces that interact with our familiar world only through gravity. In such a scenario, dark matter would not be a single type of particle, but an entire invisible ecosystem, with its own structures and dynamics, unfolding silently alongside the visible universe. These ideas may sound almost dreamlike, but they arise from a simple and unavoidable truth. We do not yet know what dark matter is, and so the search remains open, guided by observation, shaped by theory, and driven by a quiet curiosity that refuses to fade. As you listen, let this uncertainty settle gently into your thoughts, because in a way it is not just a gap in our knowledge. It is an invitation, a reminder that even now, even after centuries of discovery, the universe still holds secrets that lie just beyond our reach. And somewhere within that unseen layer of reality, the true nature of dark matter continues to wait. The deeper we move into this unseen layer of reality, the more the mystery of dark matter begins to feel less like a missing piece, and more like an entirely hidden dimension of existence, quietly overlapping with everything we know. And yet, despite how abstract this may seem, scientists have found ways to test these ideas, not just through theory, but through observation, by watching how the universe behaves under extreme conditions. One of the most revealing approaches has been to study what happens when massive structures interact, when galaxies collide, when clusters merge, when gravity itself is pushed to its limits. Because in these moments, the difference between what we can see and what actually exists becomes impossible to ignore. When two galaxies pass through each other, something unexpected happens. The stars, separated by vast distances, rarely collide. They drift past one another almost effortlessly, like two clouds of dust crossing in slow motion. The gas within those galaxies, however, behaves very differently. It collides, compresses, heats up, and slows down, glowing brightly in X-rays as it interacts. This creates a separation between the visible components of the galaxies, the stars and the gas, each responding in its own way to the collision. But the most important question is this: what happens to the mass? Does it follow the gas, slowing down and collecting in the center? Or does it follow the stars, passing through with little resistance? Observations have given us a clear answer. The majority of the mass does not behave like the gas. It does not collide or slow down. Instead, it continues moving forward, aligned with the galaxies themselves. This tells us something profound. The dominant mass in these systems does not interact through the same forces as ordinary matter. It does not experience friction. It does not compress or heat up. It simply responds to gravity and little else. This behavior is exactly what we would expect from dark matter. It reinforces the idea that dark matter is not just invisible, but fundamentally different in how it interacts with the universe. It exists alongside ordinary matter, yet follows its own set of rules that we are only beginning to understand. And yet, even with this growing body of evidence, there remains a quiet tension within the scientific community. The difference between experienced time and external time could become enormous. A round trip that spans tens of thousands of years in the wider universe might feel like only a few decades to those on board. It is a quiet kind of time travel, not into the past, but forward into the future. A one-way passage where the travelers remain anchored in their own steady flow of time, while the universe around them advances more rapidly. But as we consider this, another question begins to emerge, one that feels almost inevitable. If time can stretch so dramatically under extreme conditions, if entire lifetimes can pass differently depending on motion and gravity, then what happens at the absolute limits? What happens when gravity becomes so intense that time nearly stops from an outside perspective? What happens when the structure of space and time itself begins to break down, or at least behave in ways that challenge our deepest understanding? We have already touched the edge of this question when we spoke of black holes. But there is still more to uncover, more layers to gently unfold. Because near these extreme objects, time does not just slow, it transforms our understanding of cause, effect, and the very sequence of events. And as we continue, we will move closer to those edges, not abruptly, but slowly, allowing the mind to adjust, to settle, to begin sensing the quiet vastness of a universe where time is not fixed, but fluid and deeply, beautifully strange. As we move closer to the most extreme regions of the universe, something begins to shift, not just in the behavior of time, but in the way we think about reality itself. Up until now, We have followed time as it stretches and slows under motion and gravity, always remaining something that flows, even if unevenly. But near certain cosmic boundaries, the idea of time as a flowing river begins to feel less certain, almost as if it starts to lose its familiar meaning. Black holes, which we gently introduced earlier, are where this transformation becomes most profound. They are not simply objects with strong gravity. They are regions where the structure of space and time curves so deeply that our usual intuitions begin to fall away. And at the heart of this mystery lies the event horizon, a boundary that separates what can be observed from what cannot. From a distance, watching something fall toward a black hole is a strangely quiet experience. There is no sudden disappearance, no dramatic crossing that can be seen directly. Instead, the falling object appears to slow down more and more as it approaches the event horizon. Its movements stretch out, becoming increasingly gradual, as if time itself is being pulled thinner and thinner. Signals sent from the object take longer to arrive. Light emitted from it becomes weaker, stretched toward longer wavelengths, fading slowly into darkness. To an outside observer, the object never quite seems to cross the boundary. It lingers, suspended at the edge, its final moments drawn out indefinitely. And this is where something deeply intriguing emerges. From this external perspective, time for the falling object appears to nearly stop. Not because the object itself feels frozen, but because the path its time takes through the curved fabric of spacetime becomes so stretched that it barely progresses relative to the outside world. But as always, perspective reshapes the story. For the object that is falling, for the person or particle or signal moving inward, nothing extraordinary is felt at the event horizon itself. There is no sudden halt, no sensation of time stopping. Instead, the crossing happens naturally, smoothly, as part of its own continuous experience of time. The difference lies entirely in how this journey compares to that of a distant observer. This dual description can feel almost impossible at first. How can one observer see something slowing to a near standstill, while another experiences no interruption at all? The answer lies in the geometry of spacetime itself. Each observer follows a different path, and along each path, time unfolds in its own way. What this reveals is something subtle yet profound. Time is not a single, shared dimension that everything moves through together. It is intertwined with space, forming a structure where each path carries its own measure of duration. Two observers can begin together, follow different routes, and arrive with entirely different amounts of time having passed. Large volumes of ultrapure materials, often noble gases like xenon, are cooled to extremely low temperatures and monitored continuously. The idea is simple in principle, though incredibly difficult in practice. If a dark matter particle happens to pass through the detector and interact with an atomic nucleus, it could produce a tiny flash of light or a small release of energy. By capturing and analyzing these signals, scientists hope to distinguish a genuine dark matter event from all other sources of background noise. But this is where the challenge becomes almost philosophical. How do you confirm the presence of something that interacts so rarely, so weakly, that it may pass through entire planets without leaving a trace? Even the most sensitive detectors must contend with background signals from natural radioactivity, from trace elements in the environment, even from the materials used to build the detectors themselves. Every component must be purified to extraordinary levels. Every possible source of interference must be accounted for. and still uncertainty remains. Over the years, these experiments have grown larger and more refined. Early detectors weighed only a few kilograms. Today, they contain tons of material, increasing the likelihood that a dark matter particle might interact within their volume. And yet, despite this progress, the results have remained quiet. No definitive signal has emerged. This silence is not a failure, but it is a constraint. Each experiment that does not detect dark matter helps narrow down what it could be. It tells us that if dark matter particles exist, they must interact even more weakly than previously thought, or perhaps have masses outside the ranges we have been searching. In this way, the absence of evidence becomes a kind of guidance, gently steering the search toward new possibilities. Beyond direct detection, scientists have also turned to particle accelerators, such as the CERN, where high-energy collisions attempt to recreate conditions similar to those just after the Big Bang. In these collisions, particles are smashed together at incredible speeds, and the resulting debris is carefully analyzed. If dark matter particles can be produced in these interactions, they would not be seen directly, but their presence might be inferred from missing energy that seems to vanish from the system, carried away by something invisible. This approach adds another layer to the search, bridging the gap between cosmology and particle physics, between the largest scales of the universe and the smallest building blocks of matter. And still, the mystery persists. There are also indirect searches, where scientists look not for dark matter itself, but for the products of its interactions. If dark matter particles occasionally collide with each other in space, they might produce detectable signals such as gamma rays or neutrinos. Observatories scanning the sky for these signals search for patterns that cannot be explained by known astrophysical sources. Sometimes, hints appear, small excesses of energy, subtle anomalies that spark curiosity. But so far, none have provided definitive proof. And so, the search continues across multiple fronts, each approach offering a different perspective, each narrowing the possibilities, each bringing us slightly closer to an answer. As you listen, notice how this journey has evolved. What began as a question about distant galaxies has become a global effort, spanning underground laboratories, massive telescopes, and powerful accelerators. It is a reminder that the universe is not just something we observe. It is something we are part of, something we interact with, even if only in the faintest and most indirect ways. And somewhere, within this quiet effort, within these carefully constructed experiments and patient observations, lies the possibility of discovery. A moment when the invisible finally reveals itself, not through light, but through a subtle trace that tells us we are not alone in the matter that surrounds us. As we reach another layer of this unfolding mystery, the search for dark matter begins to feel less like a single scientific problem and more like a vast, coordinated attempt to listen to the universe in a completely new way. Because by now, it is clear that if dark matter exists, it is not hiding in one place or behaving in one simple way. It is everywhere, shaping everything, yet refusing to reveal itself directly. And so the challenge becomes not just detection, but interpretation, learning how to read the faintest possible signs of something that does not want to be seen. One of the most powerful tools in this search is not built underground or inside particle accelerators, but in space itself. Telescopes orbiting Earth and scanning the cosmos have begun to map subtle distortions in the distribution of galaxies across enormous distances. These distortions are not random. They carry the imprint of invisible mass bending space over billions of years. By studying these patterns, scientists can reconstruct a kind of invisible map, showing where dark matter must be located even though it cannot be observed directly. One major effort in this direction is the use of large-scale sky surveys, which measure the positions and shapes of millions of galaxies. Over time, these surveys reveal how matter is distributed across the universe, forming vast structures that stretch across cosmic scales. These maps consistently show the same thing. Galaxies are not the primary structure. They are embedded within something larger, something that dictates where they can form and how they evolve. That something is the dark matter network, an invisible scaffold that stretches across the cosmos. And yet, even these massive surveys only show the effects, not the substance itself. This brings us back to a central tension in modern physics. We have overwhelming gravitational evidence for dark matter, from galaxy rotation curves to gravitational lensing to the cosmic web. We can map where it must be. We can calculate how much of it exists. We can simulate its role in shaping the universe. But we still cannot say what it is made of. This gap between evidence and identity is what makes dark matter so unique in science today. It is not a missing detail. It is a missing component of reality itself. To bridge this gap, theorists continue to explore new possibilities. Some suggest that dark matter may not be a single type of particle, but part of a larger hidden sector, a parallel set of particles and forces that interact with our familiar universe only through gravity. In such a scenario, dark matter would not be isolated. It would be part of its own complex structure, possibly forming its own version of atoms, chemistry, and even large-scale structures. Others explore the idea that dark matter could be related to fields that permeate space itself, oscillating quietly in the background, influencing gravity without ever being directly detected. And still others consider more radical possibilities, where our understanding of space, time, or even gravity itself must be revised in subtle ways to account for what we observe. But despite this diversity of ideas, all paths are constrained by the same reality. Whatever dark matter is, it must reproduce the gravitational effects we see across the universe with extraordinary precision. It must explain why galaxies rotate the way they do, why clusters remain bound, why light bends as it travels through space, and why the cosmic web forms at all. Few theories can satisfy all of these conditions simultaneously, which is why dark matter remains the leading explanation. And yet, the absence of direct detection continues to remind us that the story is not complete. This is what makes the search so compelling. It exists in a state of balance between certainty and uncertainty. We are certain something is there, because the universe behaves as if it is there. But we are uncertain about its nature, because it refuses to reveal itself in any direct way. As you reflect on this, imagine the universe as something layered. At the surface, there is light, galaxies, stars, everything we can see. But beneath that surface lies a deeper structure, invisible but essential, shaping everything above it. And perhaps even deeper still, there may be layers we have not yet imagined. Each layer influencing the next, each hidden from direct view, yet all part of the same unfolding reality. This is where the story of dark matter stands today. Not at an ending, but at a threshold. A place where observation meets mystery, where measurement meets imagination, and where the universe quietly invites us to keep looking, even when the answer remains just out of reach. As the journey continues into its final phase, the mystery of dark matter begins to feel less like an isolated scientific question and more like a quiet truth woven into every corner of existence, waiting patiently for us to fully recognize its presence. Because by now, we have followed its influence across galaxies, through cosmic webs, into particle detectors buried deep underground, and even into the earliest moments of the universe itself. And everywhere we look, the same pattern returns. Something invisible is shaping everything we can see. At this point, the story shifts from discovery to reflection. Not because the mystery is solved, but because its implications are so vast that they begin to change how we think about reality itself. The universe, as we now understand it, is not dominated by what we can observe directly. Instead, the visible cosmos is only a thin layer, a luminous surface floating on top of a much deeper structure that remains hidden. This hidden structure, formed by dark matter, acts like an invisible architecture holding galaxies in place, guiding their formation and shaping the large-scale flow of matter across billions of light-years. Without it, the universe would look completely different. Galaxies might not form at all. Stars might remain scattered and isolated. The intricate cosmic web we observe today might never have emerged. And yet, despite its overwhelming influence, dark matter does not reveal itself through light. It does not shine, it does not glow, it does not cast shadows in any traditional sense. It only reveals itself through gravity, the most subtle and universal of forces. This is what makes it so difficult to study. Every attempt to observe it directly requires us to build instruments capable of detecting the smallest possible deviations in energy, motion, or light. And even then, we are always interpreting indirect signs, never the substance itself. This raises a profound question about the nature of scientific discovery. How do we truly know something exists if we can never see it directly? The answer, in the case of dark matter, lies in consistency. Across every scale of observation, from the motion of stars within galaxies to the bending of light across cosmic distances, the same invisible influence appears again and again. It is not a single anomaly or isolated discrepancy. It is a universal pattern. And in science, when a pattern appears everywhere, across different systems and different methods of observation, it becomes difficult to dismiss. Still, the human mind struggles with invisibility. We are creatures that evolved to trust sight, to rely on what can be seen and touched. So the idea that most of the universe is made of something we cannot perceive directly is deeply unsettling. It challenges intuition, it stretches imagination, and yet it also expands it, because it suggests that reality is far richer than our senses alone can capture. In recent years, scientists have continued to refine their understanding of dark matter not by directly seeing it, but by mapping its influence with increasing precision. New surveys of the sky, new simulations of cosmic evolution, and new experiments designed to detect rare interactions all contribute to a slowly sharpening picture. We now know that dark matter is not evenly distributed. It forms dense regions within galaxies, extended halos around them, and vast filaments connecting clusters across space. It is structured, organized, and dynamic, even though it remains invisible. And perhaps one of the most fascinating aspects of this structure is that it appears to have existed from the very beginning of the universe's evolution. Long before stars formed, long before galaxies took shape, dark matter was already there, quietly shaping the conditions under which everything else would emerge. It acted as a gravitational blueprint, guiding ordinary matter into patterns that would eventually become the galaxies we see today. In this sense, dark matter is not just part of the universe, it is part of its origin story. And as we move deeper into this understanding, the mystery does not disappear. Instead, it transforms. It becomes less about locating something hidden and more about understanding how something invisible can be so essential to everything that exists. This is where the story pauses, not because it is finished, but because it is still unfolding. And as we step into the final part of this journey, we move closer to the question that remains unanswered. What is dark matter, really at its most fundamental level? And why has the universe hidden it so completely from our view? As we continue into the final stretch of this journey, the mystery of dark matter begins to settle into something quieter, almost meditative, as if the universe itself is asking us not just to observe it, but to reflect on what it means that so much of reality remains unseen. Because by now, the evidence is no longer in doubt. Dark matter is not a speculative idea or a minor correction to our models. It is a fundamental part of the cosmos, shaping the motion of galaxies, influencing the formation of structure, and holding the large-scale universe together through gravity. And yet, despite its importance, it remains completely invisible to every form of electromagnetic observation we have ever developed. This contrast between influence and invisibility is what makes dark matter so profound. It is everywhere, and yet nowhere in the way we normally understand presence. As scientists continue to study it, they have realized that the challenge is not simply about detection, but about redefining what it means to observe something in the first place. Traditional astronomy relies on light. Telescopes capture photons that have traveled across space for millions or even billions of years. Through these photons, we reconstruct the history of the universe, map its structure, and understand its evolution. But dark matter does not participate in this system. It does not emit photons, absorb them, or reflect them. It is, in a sense, outside the language of light entirely. And so, to study it, we must rely on indirect methods. One of the most powerful of these methods continues to be gravitational lensing, where the presence of mass is inferred from the bending of light around invisible structures. Another is the study of galaxy rotation, where the motion of stars reveals the gravitational influence of unseen matter. And yet another is cosmological simulation, where computers recreate the evolution of the universe under different assumptions to see which version best matches reality. All of these methods converge on the same conclusion. Something massive, something non-luminous, is present throughout the universe. But even as the evidence becomes stronger, the identity of this substance remains elusive. This is where the story begins to take on a different tone. Because at this stage, we are no longer simply collecting data. We are confronting the limits of what our current theories can explain. The standard model of particle physics, one of the most successful scientific frameworks ever developed, does not include a particle that behaves like dark matter. This means that if dark matter is real, it must belong to physics beyond what we currently understand. This realization has opened the door to countless theoretical possibilities. Some propose new particles that interact only through gravity and perhaps the weak nuclear force. Others suggest entirely new forces or hidden sectors of matter that exist parallel to our own. There are even ideas that dark matter might not be particulate at all, but instead a manifestation of deeper properties of spacetime itself. Each of these possibilities carries profound implications, not only for physics, but for our understanding of reality as a whole. And yet, despite decades of effort, no single theory has been confirmed. Experiments continue to search, both underground and in space, using increasingly sensitive instruments designed to detect even the faintest interaction. But so far, the silence remains. This silence, however, is not empty. It is informative, tells us where dark matter is not. It constrains what it can be. And in science, even absence becomes a form of knowledge. As we reflect on this, it becomes clear that dark matter is not just a missing piece of the cosmic puzzle. It is a reminder that our understanding of the universe is still incomplete in a fundamental way. We have built models that describe the visible cosmos with extraordinary precision, yet those models rest upon a foundation that we still do not fully understand. And perhaps this is the most important realization of all. The universe is not obligated to reveal itself in ways that match our expectations. It operates according to principles that we are still uncovering, layer by layer, observation by observation. Dark matter is one of those layers, invisible, persistent, essential. And as we move into the final part of this journey, we will bring all of these threads together, not to solve the mystery completely, but to understand its meaning more deeply, and to see how this unseen presence quietly defines everything we think we know about existence itself. At this point in the story, as we stand between what we know and what we still cannot explain, dark matter begins to feel less like a scientific hypothesis and more like a quiet framework underlying everything that exists. Because every layer we have explored so far, from the motion of stars and galaxies to the structure of the cosmic web, from gravitational lensing to the behavior of colliding clusters, all converge on the same invisible presence. It is not something isolated or rare. It is not something that appears only in special conditions. It is everywhere, woven into the universe at every scale, from the smallest galaxies to the largest structures spanning billions of light years. And yet, despite this omnipresence, it remains completely undetectable through any direct interaction with light. This is what makes dark matter so unusual in the history of science. Most discoveries begin with something we can observe directly. A new particle is seen in a detector. A new star is photographed. A new phenomenon is measured in a laboratory. But dark matter was not discovered this way. It was inferred, slowly, carefully, through repeated inconsistencies between what we could see and what gravity demanded must be there. And over time, these inconsistencies did not disappear. They accumulated, strengthened, reinforced each other across independent lines of evidence. Today, we can describe its effects with remarkable precision. We can simulate how galaxies form inside dark matter halos. We can predict how light bends around massive clusters. We can map its distribution across the universe using weak gravitational lensing. We can even estimate how much of it exists in total compared to ordinary matter. And the answer is always the same: The visible universe is only a small fraction of what is actually there. Everything else is dark. But despite this growing clarity about its effects, its nature remains completely unknown. And this is where the story reaches one of its most fascinating tensions. Because in physics, knowing how something behaves is often the first step toward understanding what it is. Yet, in the case of dark matter, behavior alone is not enough. It does not interact with light. It does not form atoms. It does not emit radiation. It does not leave chemical traces. It exists only through gravity, the weakest but most far-reaching of all fundamental forces. This makes it extraordinarily difficult to classify within our current understanding of particle physics. The Standard Model, which describes all known particles and forces except gravity, has no place for it. So if dark matter is real, it must be something beyond that framework. Something new. Something still waiting to be discovered. This realization has driven decades of experimental effort, from underground detectors designed to capture rare particle interactions, to space telescopes searching for indirect signals, to high-energy collisions attempting to recreate conditions similar to the early universe. And yet, despite this global effort, the silence continues. No confirmed detection, no definitive signal, only increasingly strict limits on what dark matter can and cannot be. And paradoxically, this silence is not discouraging the scientific community. Instead, it is refining the search, narrowing the possibilities, guiding theory toward more precise and sometimes more unexpected directions. Because in science, absence of evidence is still a form of evidence itself. It tells us where to look next. It reshapes our assumptions. It forces us to reconsider what we thought was possible. And in the case of dark matter, it suggests that whatever it is, it may be even more subtle, more elusive, and more fundamentally different from ordinary matter than we originally imagined. As we move through this final part of the journey, it becomes clear that dark matter is not just a missing piece in a cosmic puzzle. It is a boundary marker, a signpost at the edge of current knowledge. It tells us that our understanding of the universe, while powerful and precise in many ways, is still incomplete at a fundamental level. And that realization is not a failure. It is an invitation to keep exploring, to keep questioning, and to keep looking into the invisible structure that quietly shapes everything we see. Because somewhere within that structure, beyond the reach of light, beyond the limits of current detection, the true nature of dark matter is still waiting, patient, silent, and deeply woven into the fabric of reality itself. And so, as we arrive at the final movement of this long cosmic journey, everything begins to settle into a quieter perspective, as if the universe itself is slowly dimming its brightness just enough for us to notice what has been there all along. Dark matter, after all this exploration, is no longer just a distant concept used to explain galaxy rotation or gravitational lensing. It has become something far more fundamental in our understanding of reality, a silent structure that underpins the visible universe, shaping its form from the earliest moments after the Big Bang to the present day. Every galaxy, including our own Milky Way, is embedded within an enormous halo of this invisible substance, extending far beyond the luminous stars we can see. Every cluster of galaxies is held together by its gravitational influence. Every filament in the cosmic web traces its hidden presence. And yet, despite all of this, it remains completely untouched by light, as if existing in a parallel layer of reality that never fully reveals itself to our senses. This is what makes dark matter so profoundly different from anything else we have encountered in physics. It is not just unseen. It is unseeable in principle, at least with the tools we currently possess. And that limitation forces us into a new kind of relationship with the universe, one where understanding does not always come from direct observation, but from careful inference, from patterns, from the way things move and interact over vast scales of space and time. We know dark matter is there because without it, the universe simply would not behave the way it does. Galaxies would not rotate the way they do. Clusters would not remain bound. The cosmic web would not form. Light would not bend in the precise patterns we observe through gravitational lensing. The early universe would not evolve into the structured cosmos we now inhabit. In every case, the presence of something unseen is required to complete the picture. And so, over time, what began as a puzzling discrepancy has become one of the most important pillars of modern cosmology. Yet, even as we accept its existence, we are still left with the deeper question: what is it? And this question remains unanswered not because we lack effort, but because we are pushing against the boundaries of what current technology and theory can reveal. Experiments like LUX Zeppelin continue to search for rare interactions between dark matter and ordinary matter, hoping for a single event that might reveal its particle nature. Particle accelerators at institutions like CERN attempt to recreate high-energy conditions where new particles might emerge. Space-based observatories scan the sky for indirect signals that could hint at dark matter interactions. And yet, despite all of this, the universe remains quiet in this regard. No definitive signal has emerged. No confirmed particle has been identified. Only increasingly precise boundaries defining what dark matter is not. And perhaps this is where the meaning of the search begins to shift slightly. Because in a way, dark matter is no longer just a target of discovery. It has become a mirror reflecting the limits of our current understanding. It shows us that the universe still holds layers of reality that do not easily conform to our expectations. It reminds us that even with all our progress, there are still vast regions of knowledge waiting to be uncovered. As we reflect on this, it becomes clear that the story of dark matter is not just about invisible mass. It is about the relationship between observation and reality, between what we can measure and what actually exists. It is about the humility of recognizing that the universe is not required to be simple or fully accessible to us. And yet, it is also about curiosity, persistence, and the drive to continue exploring even when answers remain out of reach. Because every piece of evidence we have gathered so far points in the same direction. Something unseen is shaping everything. Something fundamental is missing from our picture of the cosmos. And until we understand it, our understanding of the universe will remain incomplete. So as this journey comes to a close, let your thoughts drift gently through everything we have explored: the galaxies rotating in defiance of visible mass, the bending of light around invisible structures, the vast cosmic web stretching across the universe, the deep underground detectors waiting in silence, and the possibility that most of reality exists in a form we cannot yet perceive. And as you sit with that idea, imagine the universe not as something fully revealed, but as something still unfolding, layer by layer, mystery by mystery, slowly inviting us deeper into its hidden structure. Because somewhere in that invisible framework, beyond light, beyond direct observation, Beyond our current understanding, dark matter continues to exist, quietly shaping the cosmos in ways we are only just beginning to comprehend. And if you are still here, still listening in this quiet moment of reflection, gently type the number 3 in the comments to mark the end of this journey through the unseen universe.